There you go. Okay. Well, thank you very much, Irina, for the nice introduction, and also thank you very much to give me the opportunity to present our recent work, which, as you've said, is observing fundamental reaction events with ultrafast X-ray scattering. So I want to first acknowledge everyone who was part of the project. It's a fairly large collaboration, so the work presented here is the fruit of a collaboration between the groups from the Danish Technical University, Lund University, Uppsala University, Georg August Göttingen University, SACLA, the LCLS, and my home group headed by Sebastian Bosnov at the University of Gothenburg. And I've also highlighted or put in bold Anke Nimmerich, who is also responsible for the data analysis of the second half of the presentation. So, one of the main goals of physical chemistry is to understand the fundamental steps involved in chemical reactions. And I've given a few elementary steps over here, but today we'll be focusing on bond formation and scission, primarily. And in order to understand chemistry, one needs to understand what the solute does, what the solvent around the solute does, and the interplay between the solvent and the solute. So in essence, what we want to create is a detailed microscopic picture of the reaction. Now, separating the contributions of the solute, the solvent, and the interaction of the solvent-solute interactions is usually fairly tricky using conventional techniques which are used to study solution phase chemical reactions such as transient absorption spectroscopy. And this kind of brings us to the stated problem, which is we need to observe solvent-solute interactions on the timescale of chemical reactions in order to understand the fundamental chemical reaction events. But these are typically difficult to do because these solvent-solute interactions are difficult to distinguish from the bulk response of the solvent. Now, first of all, we need to take a chemical reaction that can be triggered on an ultrafast timescale if we want to have a chance to observe such events directly. So the photodissociation of diatomethane, shown here, fulfills this criteria. The system is excited by a pulse of light at 266 nanometers. The carbon-iodine bond is cleaved, and the iodine atom flies off away from the parent molecule. And at some point, the iodine atom encounters the solvent shell. And at this point, there's a certain probability of escaping the shell, and then you generate solvent-separated species. Or if it doesn't do that and it stays within the solvent shell, you have a geminate pair. And from this geminate pair species, you can form a transient photoisomer shown here. So this reaction has been studied fairly extensively with spectroscopic studies. So in that case, the dissociation step wasn't observed directly, and some controversy existed over which signals belong to the dissociation, and also what the time scale was of the dissociation. So, for example, the velocity of the iodine atom wasn't known. At later stages, the two isomer formation lifetimes were observed with approximately these lifetimes. And this lifetime here is due to the highly vibrationally excited species which result from the dissociation. And this is because the vibrational energy contributes towards crossing the formation barrier. And if once you have vibrational cooling, you don't have this excess energy to help you form the iodine bond. Now the problem is that all these signals that belong to these species here kind of and the vibrational cooling process overlapped fairly strongly in the spectra. So it's quite difficult to distinguish between these different contributions, which is why these lifetimes are sort of approximate. And as you can see, that all the species before the isomerization involve non-covalently bonded or non-covalently bonded species. So therefore, we need a technique which is also sensitive to atomic position without requiring chemical bonds. This, of course, is time-resolved wide-angle X-ray scattering. This has the potential. This technique has the potential for atomic resolution and a time resolution on the order of 100 femtoseconds. We have performed this experiment at which are analogous to pump probe spectroscopy or pump probe, the kind of experiments most people here should be familiar with. So what we do is we excite the system with a UV pulse, and then we monitor the structural changes with scattered X-ray pulses from an X-FEL source. And we do this with several delays after excitation. And by delaying the X-rays with respect to the pump, we can record the dynamics of the reactions. And so we generate difference scattering curves by subtracting the unpumped shots from the pumped shots. And as you probably know, the distances involved, or at least, sorry, the scattered X-rays reflect the inverse distances of, between the atoms. Now, reciprocal space is generally not a very intuitive space to work with. So what we do is sometimes, well, it can provide insight if you take the sine Fourier transform across the scattering vector and obtain the real space representation of the different signals. And sometimes this real space different can also trick you, so beware. But we do use this representation. So I'm not going to go into great detail how we calculate the scattering that we use in the modeling of the data, but just briefly, we consider three contributions to the different scattering. We have the solute-solute term, the solvent-solute term, which is also referred to the cage term as the cage term, and the solvent-solvent term. And in the case of the solute-solute term, this can be calculated analytically using the Debye equation. The cage term requires you to run MD simulations to get the structure of the solvent around your solute. And the latter, the solvent-solvent term, is actually requires both. And you take the RDFs that you get from the MD simulations and use them as a form factor to model the cavity that the solute forms in the solvent. And shown here in R space, in real space, are is basically the scattering library that we use to model the data. And it's basically two iodine atoms in cyclohexane. And the most prominent feature here is the solute-solute term, which increases in distance as a function of iodine-iodine separation. And the signals that you see off diagonally, let's say, belong predominantly to the solvent and the solvent interactions. So, shown here are the structural fits of the so we do the fits in reciprocal space, but I've shown here real space of the different scattering of the photodissociation of diiodomethane in cyclohexane. So the molecule is excited at T0, 0 picoseconds here. We have an increase, we observe an increase in the signal and an evolution of the scattering as time progresses. The colored bands show the different, the iodine-iodine separation distance of the different species, which are shown here. So at late time points, we have the photoisomer with, yes, that appears, and at earlier time points we observe two. Well, it's a geminate pair with two characteristic distances, and this is just the iodine atom located at different hemispheres of the around the CH2I fragment. And we have also included a solvent-separated species, which is allowed to. Yeah, we've also involved that in the fit. So first, I want to talk about the sub-picosecond timescale of the reaction. So for this shift over here, where at these timescales, we're essentially observing the physics of the chemical reaction. Since the dissociation is barrierless, we can track the real-time separation of the iodine atom from the diatomethane molecule. And since we can track the position and we have the time as a function of time, we can fit a straight line, basically, and get the velocity of the iodine atom that is separating, which is 2.1 angstrom per picosecond, or 210 meters per second. And we also know that the iodine atom travels almost an angstrom before hitting the solvent cage. Now, this is all good and well, as we can look at the physics, but I mean, what does this? What are the consequences for the chemistry of the reaction? So, from the same structural fits I showed you before, we can also obtain the amplitudes of the species at every time point. So we devised a model to fit these the time-dependent concentrations of the different species. So the model includes an initial rotation due to the dissociation. So the dissociation generates a kick on the CHI fragment. So that's a very short lifetime. And then we have an equilibration between these two geminate pair distances, which occurs around a picosecond. And then you have the biphasic decay, which occurs concurrently with the biphasic isomer formation lifetime. It seemed so. What we also found was that the solvent-separated species, that it was a bit difficult to model them because of the at least incorporate them in the kinetic model, because the amplitudes of the species was a bit too low. So the most surprising find of this was that the geminate pair lasts for a very long time. And since the formation of the isomer occurs biphasically with a very long second lifetime, this coupled with the fact that we have very low number of solvent-separated species at late times, we know that this long lifetime cannot therefore be a non-geminate recombination channel. So we thought, well, there has to be a species, an inactive, chemically inactive species, which first has to convert towards a chemically active species before it can recombine to form the photoisomer. And also what's interesting is that these formation lifetimes are fairly different from what is observed in spectroscopy. First of all, this long lifetime is not observed, and we think that this one is the true isomer formation lifetime, because we are not hampered by a convoluted spectra with the vibrational cooling process. So all are purely sensitive to the iodine-iodine distances, and therefore we can determine this lifetime more accurately. Now, we still have to answer the question about what's the deal with this long-lived geminate pair. So we decided to perform quantum mechanical calculations on the triplet state. Now, we don't believe that this inhibited species doesn't have to be a triplet state. But we use this because the triplet configuration prevents a bond formation prevents bond formation whilst keeping other relevant factors equal or reasonably equal. So shown here is the two-dimensional iodine-iodine potential energy plot, which we obtained from quantum mechanical calculations at this level of theory, which is a fairly high level. And what we find is a not insignificant energy minimum which surrounds the entire fragment and of around minus 10 kilojoules per mole, so an attractive potential around the molecule. But is this sufficient to keep these fragments together for 2.8 nanoseconds at least, or at least a nanosecond from our data? So in order to explore this, we ran two different MD simulations to estimate the fragment contact time, lifetime. So we take a regular, an MD simulation with a regular GAF, with a regular GAF potential, and we find that the contact lifetime of 30 picoseconds. And if we refine the potential against these quantum mechanical calculations shown here, we get a lifetime of 204 picoseconds, so significantly longer. So this isn't exactly, 2.8 nanoseconds, but it shows that the dispersion forces, so we believe that this energy minimum is caused by the dispersion forces of the iodine atoms, that they definitely contribute significantly towards this long-lived geminate pair. So just to summarize this part of the talk, the structural sensitivity of the time-dissolved wax experiment has enabled us to add to and revise the reaction mechanism of the dissociation of diethylmethane. From the velocity and the angular velocity of the fragments, we can calculate the energy partitioning between the translational and rotational energy of the species, of the reaction. The translational energy is surprisingly low compared to gas phase experiments. This is about 26% of, I believe, of the gas phase experiment. However, the rotational energy, the fact that it's a fairly large, or at least comparatively a large portion to us, makes sense because of the geometry of the reaction. You have this iodine atom which basically kicks off onto the dissociation reaction, generates a fairly strong kick on this fragment, which then starts rotating quite quickly. So furthermore, we found few solvent-separated species, and so most species remain as geminate pairs. Apparently, the 210 meters per second dissociation is not sufficient to allow for cage escape, or at least very little cage escape. And another major difference between this study and previous studies is that we found this long second lifetime for the photoisomer formation. It's basically a previously unobserved reaction channel. Now, unfortunately, with this reaction, since there was very little cage escape, we were not able to characterize the cage escape very well. Now, however, this phenomenon is fairly ubiquitous in chemistry, at least for dissociation reactions, and it's quite an important phenomenon in solution phase reactions. So the kind of questions you have is like, what physical properties does cage escape depend on? So, for example, solute ejection velocity, the mass of the fragment that is being ejected, is it the solvent mass, viscosity, so the hydrogen bonding, is it hydrogen bonds if the liquid is hydrogen bonding? So in order to study these dependencies, we investigated the dissociation reaction of triiodide in solution in different solvents. So we've done it in water, in acetonitrile, methanol, and ethanol. Now, this system is a great model system. It's very well studied in spectroscopy, and it has a photochemistry that is strongly solvent dependent. So that's a really good indication that we can get some cage escape going. So the reaction has been studied even more extensively than the diatomethane reaction, using a wide variety of spectroscopic techniques, time-resolved techniques. The reaction is initiated with a 400 nanometer light pulse. You get a bond scission of an iodine-iodine bond that breaks, and the two fragments fly apart. And again, as with diatomethane, you have the step where the iodine can exit or exit the parent, the original solvent shell, and penetrate the bulk, or it remains as a geminate pair in solution. So then you have, you can create a geminate recombination, or you have non-geminate recombination at much longer timescales, and you have a mysterious state X, which was observed, and they can see the lifetime, but we're not able to characterize what this state X is. So from the previous spectroscopic studies, and also liquid ultrafast electron diffraction studies, and that's a very recent paper here, this one here, very interesting paper. We can expect to observe certain a number of phenomena, ultrafast phenomena. So as with the diatomethane, you expect to observe the dissociation and the rotation of this fragment, of the I2 minus fragment. You also expect to see coherent oscillations of the product because of the visitors. Because of the coherent. The product is formed coherently, so you expect coherent oscillations, and you also, as I said before, you have the geminate recombination, which occurs roughly with 2.6 picoseconds. You have the non-geminate recombination, and the state X, depending on which study you look at, is between 12 and 40 picoseconds recombination to the ground state. We also expect ground state oscillations from as a result of visitors. So resonant impulsive stimulated Raman scattering, and also hole burning, because we excite the molecules fairly off resonance from the absorption maximum. Now, you may have noticed that we have quite a number more, a lot more different species to worry about, and also timescales and kinetic, or at least dynamic phenomena. So unlike the diatomethane, we decided we need to constrict the amplitudes with kinetic models, and also these dynamic processes during the structural fitting. And so shown here is a contour plot of the difference scattering of triiodide in water, the dissociation of triiodide in water, and this is the model that we fit to the data, which captures the main features of the data, which is good news. And I will now go through what the main features in the coming slides. So just our model does miss a couple of features shown here by the residual, but this is roughly, we approximate approximately 5, maybe 10%, or at least 5% of the total amplitude. And shown here is just the summed residual, so summed across Q, absolute residual. And usually people also enjoy seeing the stack plot of the difference scattering, And again, you can see that the fit could be better, but at least it captures the main gist of the scattering. So I'd like to begin with the structurally static species and the ground state. So considering the depleted, so the ground state, we first attempted to model the data with a common static ground state, just like the diatomethane. However, we found that the description of the early time points was not possible with this structure. So we had to introduce the what we call the initial ground state structure, or the Rizer's product. No, sorry, the whole burning. I crossed. Sorry, the whole burning. So the depletion of a specific population by the laser. And that then takes roughly 3 picoseconds to equilibrate to the equilibrium ground state. And this equilibrium ground state we obtained from this paper here, Kim et al., which includes Harry Ehe. So this equilibrium state is not fit, but and we also have these induced species. We have the this is the structural parameters of the geminate pair, the induced ground state, so the Rizer's product, and the solvent separated species. And just to show the effect of the different ground states, so you can see that there is, it's a significant difference between these curves, depending on whether you, which ground state you use. So it was definitely an important factor to take into account. So moving on to the dynamics, so the dissociation and the rotation part of the reaction. The species that, so the initial part where the iodine atom dissociates from the rest of the I2- fragment, that part is the same for both solvent-separated species and geminate pair. So the velocity, for example, is the same. We modeled as the same. And at some point, you have the time of flight, where the iodine atom hits the solvent shell. So in the case of the geminate pair, we then say, okay, that's where the iodine-iodine separation stops. And then we have the static species here, structurally static species, that continue on. And in the case of the solvent-separated species, this continues on for a bit longer. So from this, the structural, or at least the parameter that that's the free parameter, is the time of flight, but also the dissociation velocity. And we found that in water, the triiodide dissociates the fragments recede with a velocity of 520 meters per second, or 5.2 angstrom per picosecond, significantly higher than the diatomethane. And we also found a rotational lifetime of 0.82 or 0.82 radians per picosecond. Sorry, no, I got this wrong way around. Picoseconds per radians. It's a lifetime. And most importantly, we managed to determine, just by taking the ratio of these two, of the cage escape. And just quickly going to the kinetics, we found that the lifetimes of the different species correspond reasonably well with those found in spectroscopy. So most importantly is the biphasic decay of the geminate pair. So you have the short lifetime, which corresponds well with what you find in spectroscopy, which is the geminate recombination of the, and also the second lifetime corresponds well with what is known as state X. And in our case, we can model this purely with one structure, which is the geminate pair. So we believe that the state X is a vibrationally cooled I2- fragment of the geminate pair, and then which is ends up to be roughly 50% of the pairs end up as vibrationally cooled geminate pairs. And we also managed to find the lifetime of the resist product, which is 100 femtoseconds, which is a reasonable time frame for that species to decay. We also performed exactly the same modeling with the same species and kinetics and everything in acetonitrile. And this fit is also fairly reasonable. There's just the major difference here, though, is the amount of the excitation fraction is significantly higher than in water, and that is probably due to the fact that we excite more on resonance in the absorption band of triiodide in acetonitrile. So this is a summary. So we also managed to extract all the physical properties that we did for the triiodide in water in acetonitrile, and this is just a summary of a few of them. And I want to draw your attention to the velocity. So in the case of acetonitrile, this velocity is significantly higher than in water. This is coupled with a slower lifetime, a rotational lifetime, as compared to water, and also and these two parameters together is interesting because we know from spectroscopy and previous synchrotron experiments on triiodide, the dissociation of triiodide, that the ground state structure of triiodide is more linear and symmetric in acetonitrile than in water. So if the molecule is more linear, you would expect that more energy is partitioned into the translational energy than into the rotationals compared to water. So that's a nice, that adds up nicely. And also what correlates well with the velocity, increased velocity, is the increased cage escape. Here. The increased cage escape, percentage cage molecules that escape the cage. So yeah. Now, of course, and I've also put the diatomethane here as a reference. Now, of course, two solvents is not really sufficient to really say much about what is actually important for this cage escape. I mean, it seems logical that, of course, the velocity matters, but other parameters such as the microviscosity of the solvent could very well play a role, and we just need to. We are working on the modeling of triiodide in dissociation of triiodide in ethanol and methanol. So hopefully we can get at least four solvents, which should give us a better picture of what is important for determining this this ratio. And to compare with the liquid ultrafast electron diffraction, they found a cage escape of 0.26 with a plus or minus 0.1 with a 10% error bar, and that in water, so that corresponds reasonably well, which is good. And also the cage escape from spectroscopic studies is also fairly is within this ballpark. So that all adds up fairly well. And with this, I would like to conclude. So we investigated the dissociation of triiodide in water and acetonitrile. We have determined the velocity of the fragments as a result of the dissociation, and also the rotational lifetime. From these constants, we can get these parameters. We can get the translational and rotational energy partitioning, and in case of triiodide, if you remember that in diatomethane, the partitioning is more equal between the two. And this has we believe this has a lot to do with basically the geometry of the reaction. So that it's nice to see that we can do that. Other parameters that we found was most importantly, we managed to find out what state X is, which is a vibrationally cooled geminate pair, which recombines slower to form the ground state. And more generally, we've observed the real-time sub-picosecond structural evolutions of photodissociation reactions. We've made a start with studying the solvent dependence on the dissociation reaction, and therefore the cage escape phenomenon. And we've been able to identify species which have not been characterized with spectroscopy because of the structural sensitivity of the TL wax, because time-resolved wide-angle X-ray scattering is sensitive to atomic distances and not to electronic states, which require chemical bonds generally. And so I think we can amend the original statement that with time-resolved wide-angle X-ray scattering, we can observe solvent-solute interactions on the chemically relevant timescales. And before I leave you, I just want to plug some of our research at the BioCars beamline, which we, of course, did with Irina and Robert and others. But this is a completely different experiment, different system. We did some temperature jumps on proteins and also some optical experiments on time-resolved experiments on phototropin. And with this, I want to thank you for your attention.